Welcome to the Explainer. Today, we're going to tackle a question that seems super simple, but the answer? Well, it's going to flip what you think you know about strength completely on its head.
Okay, so which one is it? A rubber band or a steel beam? Come on, be honest. Your first instinct, your gut, is probably screaming the rubber band, duh, right? I mean, that's what we've all thought forever, but what does physics actually say?
You're not going to believe this, but the answer is steel. Yep, steel. And to get why this isn't crazy, we've got to look at what's really going on inside a solid object when you start pushing or pulling on it.
So, anytime you push, pull, or twist something and it changes its shape, that's called deformation. Simple enough? But here's where it gets interesting. There are actually two totally different ways something can deform.
First, you've got elastic deformation. This is the one you know well. You stretch a rubber band, you let go, and snap! It goes right back to how it was. It's temporary. Then you've got the other kind, plastic deformation. Think about squishing some clay in your hand. The shape you make, well, it stays that way. That change is permanent.
Okay, so whenever you try to change an object's shape, it doesn't just sit there and take it. On an atomic level, it's fighting back. It's resisting. And in physics, we have a name for that internal fighting back force. We call it stress.
And here's the crucial part. Stress isn't just about how hard you push, it's about how concentrated that push is. Think about it. A huge force spread out over a giant area might not do much, but even a tiny force focused on a pinpoint, that can create a ton of stress.
So if stress is the cause, the material fighting back, then strain is the effect. It's how we measure how much the object actually deformed. It's a number that tells us, okay, how much did this thing really change compared to how big it was to begin with?
And check this out. Because strain is just a ratio, like change in length divided by the original length, the units, like meters over meters, they just cancel each other out. So strain doesn't have any units. It's just a pure number. A strain of, say, 0.1 just means the object stretched by 10%.
Okay, so back in the day, a brilliant scientist named Robert Hooke figured out something really cool about all this. He realized that for most stuff, there's a super simple relationship here. You double the stress, you get double the strain. It's a straight line. But, and this is a huge but, that only works up to a certain point. After that, all bets are off.
So, to make this a neat little equation, we use a constant. We'll call it K. And this K is called the modulus of elasticity. You can think of it like a material's unique fingerprint. It's just one number, but it tells you everything about how hard that material fights back against being stretched or squished.
And boom, right here. This is the key to our whole puzzle. See, in everyday life, when we say elastic, we mean stretchy. But in physics, it's the complete opposite. Elasticity means toughness, rigidity. It's all about how much a material hates changing its shape and how perfectly it snaps back when you let it go. So a material that's more elastic is one that puts up a way bigger fight. For just a tiny little bit of strain, it generates a huge amount of internal stress. It's basically screaming, no way, I am not changing my shape. Okay, let's look at the actual data. This is the modulus of elasticity for a few things you know. Wood is down there at 13, glass is at 65, and then look at steel. It's all the way up at 200. It's not even close. That number is proof of just how incredibly tough and resistant steel really is.
So let's bring it all home. A rubber band? Sure, it stretches easily, but it also gets permanently stretched out pretty easily too. A steel beam, on the other hand, it can take a massive, massive force and still spring back to its original shape perfectly. That incredible resistance and that perfect return, that's what physicists mean by elasticity.
But what if we just keep adding more and more stress? I mean, everything has a breaking point, right? To see what happens next, we need to look at something called the stress-strain curve. It's like the entire life story of a material, from its first stretch to its final snap.
So, at the start of its story, our material is a model citizen. It follows Hooke's law perfectly. Stress and strain go up together in a nice straight line. But then it hits point A, the proportionality limit. This is where it breaks its first promise. The relationship isn't a simple straight line anymore. The line starts to curve.
And just after that, we hit point B. This is the big one, the elastic limit or yield point. This is the point of no return. The material basically throws its hands up and says, all right, I give up. Go past this point and it's permanently changed. It's never, ever going back to its original shape.
But even though it's permanently bent out of shape, it's not done fighting. The stress keeps going up and up until it hits a peak at point D.
We call this the ultimate tensile strength. This is the absolute most stress it can possibly take before it starts to physically fail, to get thin in one spot, getting ready to break.
And then, that's it. After hitting its peak, it just can't hold on anymore. The strain suddenly shoots up, even as the stress might drop a little, until it hits point E, the fracture point. It snaps. The end.
So what's the big takeaway here? 3 things. First, elasticity in physics isn't about being stretchy. It's about being tough and resisting change. Second, that's why steel is way more elastic than rubber. It has a much higher modulus. And third, every single material has this dramatic life story, a breaking point, and we can see it all laid out on its stress-strain curve.
This leaves us with one final question. If elasticity is really all about resisting change, how does that principle influence the design of everything around us? From skyscrapers built to sway in earthquakes, to the spacecraft that have to survive the incredible forces of launch. It's not just a cool paradox, it's the fundamental science that lets us build our entire world.